Hello everyone. In the last session, we learned about beam element and the procedure to obtain the stiffness matrix. Similarly, if you want to look at a frame member like this, then this frame member will have degrees of freedom like this, and even in the axial direction. Now this will be 2, this will be 3, 4, this will be 5, and this will be 6. So it will have 6 degrees of freedoms. Now to find your stiffness matrix for this case, you can see here that the frame element is a combination of bar element and the beam element. So what you have to do is you have to combine the stiffness matrix for your bar element with the stiffness matrix of the beam element in their respective degrees of freedom. So what you'll get is you'll have a big matrix which will be a 6 by 6 matrix. So 1 1 corresponds to your force in the upward direction due to unit displacement in the same direction upward. Now this one corresponds to your beam value, so this will be equal to 12 EI by L cube. And 2, it will have no effect in the axial direction, and 3, this is the moment, so it will be 6 EI by L square, and 4, it will be minus 12 EI by L cube, and 5, no reaction, and 6, it will be 6 EI by L square. Now if you are looking at the second one, which is the axial one, it has no influence on this or this, therefore this will be equal to 0. 2, it will be AE by L that we obtain for the bar element. This will be 0, this will be 0, this will be minus AE by L, and 6, it will be 0. For the third one, this will correspond to your moment here, F3, which will correspond to your F2 in the above here. It will correspond to this one. So you just copy the values down to the respective degrees of freedom. So it will be all the values written in blue correspond to the beam, and all the values written in red will correspond to the bar. So this is your stiffness matrix for a frame element. Now let's dig a little deeper in the frame elements. Now the frame elements can be column or beam, where column you'll see that it is oriented perpendicular to the horizontal axis, and you have your beam which will be oriented in the direction of your horizontal axis. If this was our reference axis, now the angle that is made by column with the x-axis will be 90 degree, and of the beam will be 0 degree. In some of the cases, you may get a frame which may be inclined like this. Now here, this is our column, this is a beam, this is our another column. Now here, this angle will be less than 90. Let's say this is alpha, and this column makes an angle of 90 degree with the horizontal, and this beam makes a 0 degree with the horizontal. Now in this case as well, we have to form a generalized stiffness matrix. This stiffness matrix here will work for a beam that is oriented horizontally with the x-axis. So here your alpha will be equals to 0. This will only be valid for a frame element that is parallel to the horizontal axis. Now for this one, let's say we have a frame element that is inclined like this with the horizontal let's say this makes an angle alpha. This is your x direction, this is your y direction, and this is our frame member. Now in this case, the frame will have degree of freedom in this direction, in this direction, and this direction. It will have degree of freedom in this direction, in this direction, and in this direction. I'm writing these directions as per the local orientation of the frame member, because what we have done is we have formed our stiffness matrix for a beam element or a frame element, where you'll have your F1 degree of freedom 1 is perpendicular to the local axis of the beam. And we have developed the stiffness matrix for the bar element, in which the force acts in the axial direction, or the degree of freedom is along the axis of the bar element. And we also have our moment here. Here also, now if we rotate this one by an angle alpha, which is like this one here, then you'll see that everything rotates like this. Therefore, we're writing these axes, these degrees of freedoms, as per the local orientation of the frame element. Now what we have here is, this will be our local degrees of freedom. So let's label them as U1 small f1 and U6 f6. Now you'll see here that I have labeled these degrees of freedom differently than what I did here. What I have done is I have labeled this one as 1, this one as 2, and this one as 3. This one will be 4, this one will be 5, this one will be 6. So the columns and rows of this matrix here will shift according to the degrees of freedom. If you have a frame like this and a frame like this, then to add the forces, we have to orient the forces in the same direction for the global forces as we did in the truss. So we have to find components of each forces in the x direction, in the y direction, and the rotation along the z direction. Now to do this, for the global system, this is our x, this is our y. If this was our frame, now for the global one, let's say this direction here, this degree of freedom here, capital U x1, and force is fx1. And for the global y, in this one, that will be U y1 and fy1. And for the rotation here, that will be ur1 and fr1. Similarly, ur2 and fr2. As we did in truss, we have to resolve all the global forces and displacement into the local system. For example, if we have beam like this, and globally we're applying ux1 in this direction and uy1 in the vertical direction, and the angle here is alpha, and you know that this direction here is u1 locally, then your u1 will be equal to ux1 cos alpha plus uy1 sine this will be your u1 in this direction. When you apply a global displacement of ux1 in this direction and uy1 in this direction. Similarly, your u2, this direction here, will be equal to, this here is 90, this angle here will be 90 minus alpha, therefore this angle is alpha, therefore you'll get ux1 cos of 90 minus alpha, which will be sine alpha. Yep. And then you get your cos alpha as well. And then what you'll have is you get your u3. Since this is a rotation about z-axis, and for the global and the local axis, z-axis is the same, therefore your u3, which is this one, equals to ur1. Similarly, now you can see here that the left hand side is composed of the local degrees of freedom, and the right hand side is composed of the global degrees of freedom. Therefore, this gives us a relation between the local degrees of freedom and global degrees of freedom. We can write this in a matrix form, and this matrix here is known as the transformation matrix, because this matrix is used to transform the values of the global coordinates into local, or local coordinates into global. This is equation number 1. Similarly, when you look at the forces, what we do here is we write the global forces in terms of local forces. Now if you do the similar procedure like above, what you'll get is, you can see here that the left hand side will have global forces, and on the right hand side we have the local forces. Now if you form a matrix, what you'll get is, now you'll be able to see that this matrix here is the transpose of the transformation matrix we obtained earlier, which is this one here. Transpose means that the row of this one will be equal to column of this one. Our local equilibrium equation will be, now we have to transform this into global. To do this, let's multiply both sides of this equation by transpose of transformation matrix, or T matrix, because if you look here, you'll see that if this is F global, will be equal to T transpose times F local. You'll find that your global stiffness matrix is given by this equation here. So your K global for frame element oriented in any direction will be given by, now this K local refers to all the stiffness matrix we have derived earlier. Now this one may be for bar element and beam element. Now to find a global matrix of a frame, which may look something like this, then you have to find your K local for each of them, and you have to find your transformation matrix for each of them, and then you have to find your global matrix for each of them, and then add these together depending upon the degrees of freedom. So it is a very lengthy process, or this one can be of frame element as well, which is a combination of these two. Now let's do a numerical example for the frame element. Let's say we have a frame, load applied here, which is 10,000 pounds, and a moment applied here be 5,000 pounds inch. Let's name the elements. So we'll have a node here, a node here, a node here, and here. Now let E for all the elements equals to 30 into 10 to the power 6 psi, and area for all of them be 10 inch square. The moment of inertia for element 1 and element 3 are equal inch 4, but for element number 2 it is 100 inch 4. Now the problem here is to solve the frame, or you have to solve the displacements and reaction forces. At first, what to do is we form a table which will be element, and then we have our angle alpha, and then L equals to cos alpha, M equals to sin alpha. So for element number 1, if you look at element number 1, you'll see that your alpha, which is this angle, is 90 degrees. For element number 2, angle is 0 degrees, and for element number 3, you have to look from here to here. What I'll do here is I'll add another section, another column here, which will say nodes. So for element number 1, you'll be looking at node 1 to node 2. For element number 2, you'll be looking at node 2 to node 3, and for element number 3, you'll be looking at node number 3 to node number 4. So this is your direction of the element orientation or local orientation of the element. Now alpha for element 1 is 90 degree, for element 2 is 0 degree, but for element 3 is you have to get the angle from here like this, be equal to 270 degrees. Now your L will be 0, 1, 1, 0, and 0, minus 1. So we obtain L and M values, or cos alpha and sin alpha values, for each of our element. Now this will help us to find the transformation matrix. Now your local stiffness matrix for a frame element will be given by this matrix with the degree of freedom labeled here. So please refer to the degrees of freedom here and positive sign convention of the degrees of freedoms for this matrix. Now you can obtain your local stiffness matrices for each of them. You can obtain K1, K2, and K3. And similarly, you also have to obtain your transformation matrix for element 1, element 2, and element 3. So this will be your transformation matrix where L equals to cos alpha and M equals to sin alpha for each element. Now what you have to do is you have to find the global stiffness matrices for each of the element. Then you have to add them together to form the one huge global stiffness matrix for all the system depending upon the degrees of freedom. Now here, for this frame element, you have three degrees of freedom here, three here, which will be same here, three here, and three here. So in total you have 4 into 3, that equals to 12 degrees of freedom. Therefore your matrix will be a 12 by 12 matrix. Then you form your global force factor, which will be equal to your global stiffness matrix times of global displacements. And here you put your boundary conditions. Now this one and this one are fixed, therefore so you have to solve for these displacements. You can see here the forces applied in the frame are only in direction Fx2 and Fr3. Therefore now you only have to look into these degrees of freedom and put the matrix here, and you can solve for your displacements and rotations. And if you want to find your reaction forces, then you're going to take this value and substitute it here, and you obtain your F global forces. So this is the way you solve for your frames. I'm not sure if they will ask you in the examination, because the matrices here will be very big. I believe they only ask you to solve for beams or trusses. But if you want to look at another problem for the frame element, you can go to chapter 1.6, that is frame modeling. For this type of problem we may have to use Excel or MATLAB to solve. So this is it for today. In the next session we'll be looking into the coordinate systems, which comprises of local, global and natural coordinate system and the relation between them, and we'll learn how to obtain the stiffness matrix based on these natural coordinates. And we'll also look into the 2D elements such as the plate elements. Thank you for watching till the end. See you next time.